Okay, how about now?
Yeah, we can see your presentation mode.
Okay, now if I move. No.
It's still the first slide.
Okay, so I
Now we
think we
see the
just
second
use
slide.
the slide I sent it to the organizer.
The organizers will change for you.
Okay, good, thank you.
Okay, then go ahead.
Okay. Okay, so sorry all this technical trouble. I also don't understand what's going on here, but anyway. So yeah, today I'm going to talk about this topological superconductors in van der Waals heterostructures, and we are going to characterize it using scanning tunneling microscope. So I think the topological superconductor is not something. Second slide. So it's not something new for. Sorry. Should I continue? Sorry, should I continue?
Just go on. Yeah.
Okay, so yeah, second slide, please. So yeah, not something new for this audience. So basically, it's a new type of superconductor. It has a gap in the bulk, but it has this boundary modes, metallic boundary mode, which is protected by that gap. And interesting, I mean, importantly, this boundary mode hosts so-called Majorana zero modes. It's believed to at least, and the Majorana zero mode is the main building block for quantum computing. However, in these materials very rarely exist in nature, but we can achieve this material in an artificial way by combining superconductors, magnetism, and spin-orbit coupling to achieve this kind of engineered band structures. Next slide. So there are three main ingredients in topological superconductors to get superconductors. Let's start with simple parabolic band. If you add Rashba spin-orbit coupling, you basically left this spin degeneracy, except the one point where the Rashba goes to zero. Now, if you add Zeeman term into this system, you left that rest of the spin degeneracy and open a gap. Now, if you add superconductors, basically you just get symmetric band due to the particle hole symmetry. And the main important condition in order to enter the topological superconductor is where your chemical potential is. In order to enter the topological superconductor, your chemical potential has to be in the gap, which is defined by this the magnetization gap. So here schematically shown a simple topological, so-called topological phase diagram. In order to enter, we need to be in this red region in here. Next slide. So this has been experimentalized in different systems. In the one-dimensional case, the famous example is this atomic chains, which is self-assembled or atomically perfectly constructed by STM scanning tunneling microscope. And in these systems, the Majorana zero modes should leave at the end of the chain. However, next slide. However, this is not something only limited. Next slide, please. Not something limited by one-dimensional case. It's also been reported in two-dimensional case, where you deposit island of ferromagnetic islands on superconducting substrate. Then if you look for with STM, you should still see the age states at the age of magnetic islands. The difference here is that in the one-dimensional case, you are tunneling into the single states. In two-dimensional case, you have band of states. So you have many states around circulating around your topological interface. The next slide. So we would like to do it using van der Waals materials. As you know, the van der Waals material, you have many different tuning parameters. For example, the alignment between the layers, or you can also use you can also make simple devices out of it. So here we use niobium diselenide as our superconductor, which is layered superconductor, as we heard from previous talk. And our magnetic materials is here we use the chromium tribromide, and which which is newly discovered two-dimensional ferromagnets. And if all the conditions are satisfied, we should expect the boundary modes, and that can be studied using scanning tunneling microscope. Basically, I'm going to focus these two papers we recently published. Next slide, please. So this is how monolayer chromium bromide looks like on niobium diselenite. We use molecular beam epitaxy to grow our sample, and as you can see, this is the STM scanning STM topographic images, and we have here is a zoom in atomic resolution of the monolayer chromium bromide. As you can see, besides the atomic resolution, you can also see some patterns, which is called moire pattern, and basically it comes from the lattice mismatch between these two different materials. And we also checked it is magnetic properties using MOC measurement, magnetic optical Kerr microscope. And as you can see very nice hysteresis loop here with different temperatures. And from this, we can get the Curie temperature, which is in the range of 60 Kelvin. And all the experiment we did is done at 300 millikelvin. So this temperature range is it's okay for us. So if you want interested more details about the sample growth and other characteristics, please go to this publication. Next slide, please. So as I said, the most difficult condition to satisfy the to enter the topological phase is where the position of the chemical potential. In the niobium diselenite case, niobium diselenite has a triangular lattice, and the topological phase should appear those high symmetry points, mainly gamma and mk, and where the Rashba goes to 0. So, and you can also see where this this high symmetry point is located by calculating the band structures. In this particular experiment, we don't have external gate to control the Fermi level chemical potential of our system. Therefore, what we are looking for is the high symmetry point, which is very close to the Fermi level. So, according to the DFT here for the monolayer case, the high symmetry point is here is M point, which is close to the Fermi level. And however, as you can see, this point is also lower than like 250 millielectrons below the Fermi level. However, what we are using is the bulk materials, and in the bulk case, this M point is a little bit closer, but it is still 50 to 100 millielectron below the Fermi level. So therefore, we still need some kind of doping to enter the topological phase. So we can also check experimental whether we have this kind of shift or not by looking at the Sds spectroscopy. Here, this Sds spectra taken on bare niobium diselenite, and this peak is correspond to the D band of the niobium in the niobium diselenite. As you can see, when we measure the same spectra through the chromium bromide layer, this spectra is shifted. And this shift we can also study systematically across the boundary between chromium bromide and niobium diselenite. And from this, we can get the overall shift is something around 80 millielectron volt. And this is really puts us very close to where we should be. Next slide, please. And here, there's some low bias spectroscopy. As you can see, this is the bare niobium diselenite superconducting gap you already saw before. Now we can also measure the same spectra on top of the chromium bromide, and here this red spectra is through the chromium bromide. As you can see, these two spectra are similar. However, in the chromium bromide spectra through the chromium bromide, we have extra peaks inside the gap. And in order to see this more clearly, now I can subtract the background spectra from this, and then I get the third data spectra here. Now, as you can see, we have some sort of gap, and this gap I for now, I call it topological gap, but I have to prove to you this is indeed a topological gap by looking at the age of the sample. If this is the gap is related to topological gap, then when I go from a trivial superconductor to the topological superconductor, and this gap has to be closed, and I should expect some kind of age stays at the boundary of this system. Next slide, please. Now, this is another spectra, another island, and this is in the middle. It's the Sds spectra. As you can see, at the age of the sample, we have very strong enhancement of the density of states. And interestingly, this enhanced states lives in this region, the red curve over there, the gap which is defined by the topological. We can also look at how this states varies in space, and this is the map taken at zero bias conductance map. As you can see, this states really localized only at the age of the sample, and this is a very nice indication. This states probably the topological. This system probably topological system. Next slide, please. In STM, of course, we can measure a different island with different shape and different at different tip conditions, and all the cases we only observe these states for all the islands, and it doesn't matter what kind of shape and orientation of the island we have. Next slide, please. So in order to say something about this is related to topological superconductor, first thing we need to check is this state kind of related to at least superconductivity of the sample. For that, we just remove the superconductivity from the equation or destroy the superconductor by applying external magnetic field. Here we are applying 4 Tesla external magnetic field, and which that kills completely the superconductivity in the niobium diselenide. As soon as we destroy the superconductivity, the states which is at the age it completely disappears. And here the map, and here some line spectra which taken across this island. And this is eliminates some trivial states, trivial electronic state, which is not related to superconductors, and also it's also eliminates so-called Kondo effect, which is the conduction magnetic impurity screened by conduction electrons, and that states should exist even if the superconductivity is gone, or splits under the external magnetic field, depending on what kind of reads the peak has. Next slide, please. So we also did some comparison between theory and experimental results, and this is the results are shown here. I don't want to go to all the details of what the quantitative and the qualitative agreement between the theory and the experiment, but what I want to say is what the experiment doesn't reproduce. Our experimental results, the theory doesn't reproduce. As you can see here, even if you have this kind of straight age of the age, but we still have some sort of modulation on top of the age state that we see. And this modulation exists for all different islands. Next slide, please. And which is shown here. So the one can think of, and in these materials, we have also this moire pattern. So the main question now is there any relation between this moire pattern and the modulation of the age states on the system? Next slide, please. So here the very simple schematics of what is a moire patterns. Moire pattern basically the interference pattern which rises between two different layers if they have a different lattice mismatch or misaligned for respect to each other. And this lattice mismatch or misalignment gives you a new moire lattice, which is much larger than the original lattice constant you have in the system. And as a result of this, the original electronic band starts to fold, which folds the electric band into a so-called moire Boolean zone, its own Boolean zone. And this opens this folding the band, and it opens also some small gaps, which is called moire mini bands, mini gaps. And as a result of that, you create some sort of a periodic potential on top of your material, and this will modify the pristine electronic property of your original material. Next slide, please. Now the question is how this affects how one can apply this into the topological system. So let's look at in the very simple one-dimensional case. So in the one-dimensional case, your topological states appears at this green regions where on top or bottom of your parabolic band. And over there you have this helical spin states. That's why you have topological states. But in the middle of there, there's no topological region. This region is the forbidden, or there's no topological region in between this top and bottom of the band. Now, if you apply some sort of moire modulation, this modulation can be electrostatic modulation between the two different materials, or exchange coupling modulation. This exchange coupling comes from the superconductor and the magnetic layer on top. So then if you turn on this, as I said, it folds your band, opens the mini moire band. And the result is much more clear if you look at the topological phase diagram. Now, when you turn on the moire, you create new regions, which is not exist without the moire. That region now hosts the topological state. So this, by creating a moire into your system, you create new topological regions. That is the kind of regions that's trivial without the moire. Next slide, please. So now we can simply extend this into the two-dimensional case. Again, this is the triangular lattice, and this is 3 different high symmetry points, which gives you topological superconductors. And in particularly without the moire pattern now, in particular without the moire pattern, especially close to the charge neutrality point, you don't have any states, regions that host topological states. But if you turn on the moire, and I'm simply here zooming into that region, now if you include the moire, now you create new topological regions that host topological phases. So again, the moire pattern creates new region that can host topological states, and this is only exists because of the moire. So next slide, please. How we can detect do you have any modulation or not? So the first thing we can look at is the conduction band of chromium bromide, and here the STM topographic image. This is the tunneling spectra in the large bias. What we are looking at here is the conduction band on chromium bromide. As you can see, this conduction band exactly modulates as a periodicity of the moire. You can also look at in 2D case here in the different maps, and as you can see, for example, in one bias, the region one bias map, the dark region turns into bright region, and from this modulation, we can estimate the magnitude of the modulation is around 50 millielectrons.
You have 1 minute left.
Yeah. Okay. So now the question is, next slide, please. Next. One more next. Yeah. So now the question is how this thing related to the is there any correlation between the topological band and this moire modulation? As you can see here, some maps and interestingly, we have very strong modulation when we cross when you hit the topological band, and this modulation only exists exactly at that band and not outside or inside of the spectrum. And we simulated this simply by modulating the exchange coupling between superconductor, and we see when we hit the band, we have strong localization. Where outside or inside, we don't have localization. Next slide, please. This is my final slide. As it turns out, this modulation also affects affects the modulation at the edge. As you can see, when we have inside at the topological band, we have some small modulation inside of the sample, and this modulation exactly matches with the modulation of the moire when we go when we look at zero bias conductance. And our theoretical calculation also nicely reproduce this result. With that, sorry for all the difficulties, and I hope I convince you that the van der Waals materials are one of the way to engineer topological superconductors, and we have a more parameters to tune and very interesting physics. So thank you. Finally, thank you very much, and I have some positions open if anybody interested in to join the group. Thanks. Sorry for the again. Yes, any questions I can.
Yeah, thank you very much, Shawulienu, and I'm sorry that we had these problems. Thank you for the beautiful talk, so I think it's time for questions. Anybody? Yeah, there is one question there.
Thank you very much. My question about the chemical preparation of this interesting material. Why you prepare this film?
Sorry, your question is why I prepare the film or how I prepare the film?
The question is how the film is prepared, how the structure is prepared.
Okay, so how I prepared the, okay, yeah. As I said, we use MB, molecular beam epitaxy, to grow our chromium bromide, and particularly, so we didn't grow the niobium diselenite, but we can also grow niobium diselenite using MB. So I don't know you are familiar with MB technique, but it's basically you just spray paint with atoms. Basically, you just provide the metal atoms or the chalcogen or the bromine or whatever the next element is. You evaporate them on top of preheated substrate. The substrate temperature usually matters what kind of final product you get. And the nice thing with van der Waals is you don't limit it in this kind of lattice mismatch. So the van der Waals, if it actually doesn't, I mean, the lattice mismatch is not that important. So they can just grow epitaxially. But of course, if it's a real, like the 3D material, not van der Waals material, then the lattice mismatch matters. I hope that answers the question.
Thank you.
Yeah, I also have a question. So you showed that for these edge states, you get a peak usually, and not because in principle, for these one-dimensional edge states, you do not only have particular energy of your Majorana modes, but they are distributed all over the topological gap, right? So what is your explanation why you see a peak and not some? Yeah,
you are right. So it's not necessarily you should observe the peak, and there's some theoretical work. I mean, if you based on theoretical calculation, if this dispersion slope of the dispersion is linear, then you should get constant dose, not the peak. But as you can see, this peak is a little bit broad. It's broad because of you are tunneling into band, not single states. But as you know, we are not measuring dose. We are measuring aldose, basically. So the aldose is not exactly the dose, but it's really depend on what kind of material, I mean, the material properties. And you usually not get exactly linear dispersion. I mean, the aldose can change dramatically if you have not linear, a little bit kink in the dispersion, then you start to get peak. So in that sense, you are right. It's not necessarily you get a peak. You can also get a just constant step. But in this particular system, we mostly get a peak, very broad peak, the sharp peak.
Yeah, thank you. Could it also be that you have some kind of confinement of your Majorana modes in the edge, which lead to confined states and discrete peaks?
Yeah. Okay. This is something we didn't check properly. So that means the island size matters. I think the confinement in that sense, what you are saying. As you can see, we measured our island size is at some of the slides, but this one we didn't check it properly. So just looking at the Myron with the different sizes, really follow from small to big, and try to look at the evolution of the peak. But this we didn't try. But yeah.
Okay, thank you. Is there any other question from the audience or from online visitors? No? Okay, then let's thank Shawulienu again. Thank you for your talk.
Okay. Thank you, and sorry for all the technical
No
problems.
problem. And by this we end this